In 1874, George Cantor mathematically demonstrated that infinity is not a single value, but exists in different sizes. The smallest infinite size is Aleph null, which represents the cardinality of the set of all natural numbers. Two sets have the same size if their elements can be paired in a one-to-one correspondence, called a bijection. Cantor used a diagonal argument to prove that the set of real numbers cannot be mapped to the natural numbers. The size of the set of real numbers is known as the cardinality of the continuum, denoted by the letter C. The power set of any set contains all its possible subsets and always has a strictly higher cardinality.
Mathematically, the cardinality of the continuum is exactly 2 raised to the power of Aleph null. The continuum hypothesis conjectures that there is no set with a cardinality strictly between the integers and the real numbers. The hypothesis asserts that the cardinality of the continuum is exactly Aleph 1, the very next size after Aleph null. In 1900, David Hilbert placed the continuum hypothesis as the first on his list of 23 open mathematical problems. Modern mathematics relies on the Zermelo Fraenkel axioms, which provide the formal rules for how sets behave and interact. Including the axiom of choice creates the standard system known as ZFC, the framework for nearly all modern mathematical proofs.
A statement is consistent with a system if its inclusion does not lead to a logical contradiction within that system. In 1938, Kurt Gödel created the constructible universe L, a model where every set is built in a definite order. Gödel proved that the continuum hypothesis is true within this constructible universe, demonstrating its consistency with the ZFC axioms. While Gödel showed the hypothesis could be true, he did not prove it must be true in every possible mathematical universe. In 1963, Paul Cohen developed a revolutionary technique called forcing to construct new types of mathematical models. Forcing adds generic filters to an existing model to create a larger model with specific desired properties.
Using forcing, Cohen built a model where the continuum hypothesis is false by adding many subsets to the natural numbers. The combined work of Gödel and Cohen proved that the continuum hypothesis is independent of the ZFC axioms. This means the hypothesis can neither be proven nor disproven using the standard tools of contemporary logic. Independence suggests that there are multiple valid set-theoretic universes, each with a different answer to the problem of infinity. Logicians seek new axioms beyond ZFC to determine if there is a single natural model that reflects mathematical reality. Large cardinal axioms postulate the existence of infinities so vast they cannot be reached by the standard set operations.
Hugh Wooden developed omega logic to analyze whether certain truths about the continuum are invariant across different forcing extensions. Forcing axioms, like Martin's maximum, suggest that the universe is saturated with as many sets as logically possible. Under the assumption of Martin's maximum, the continuum hypothesis is false, and the size of the continuum is Aleph 2. The ultimate L program aims to extend Gödel's constructible universe to incorporate all known large cardinal axioms. In the theoretical framework of ultimate L, the continuum hypothesis would once again be true, reflecting a simpler universe. The goal is a complete set of axioms where every meaningful question about the size of sets has a definitive answer.
Independence results force us to reconsider if mathematical objects exist independently or are merely constructs of our formal systems. The Beth sequence defines cardinalities by iteratively taking power sets, starting from Beth null, which equals Aleph null. By definition, the size of the continuum is Beth 1, but its location in the Aleph hierarchy remains unknown. Related to the continuum is the singular cardinal hypothesis, which governs the behavior of power sets at even larger scales. Standard arithmetic rules fail for transfinite numbers, where Aleph null plus 1 is still equal to Aleph null. The axiom of choice implies the well-ordering theorem, stating that every set can be arranged in a linear order. While cardinals measure the size of a set,
Ordinals describe the order type of its elements when well ordered. Hartog's theorem proves that for any set, there is always a least ordinal that cannot be mapped into it injectively. The Skolem paradox highlights that even uncountable sets must have countable models within certain formal logical systems. As of 2026, researchers are investigating the compatibility of the inner model program with strong forcing axioms. Descriptive set theory examines the hierarchy of subsets of the real line, providing clues about the continuum's deep structure. The axiom of determinacy offers an alternative to the axiom of choice, leading to a very different view of infinity.
The unsolvability of the continuum hypothesis remains the primary battlefield for the philosophical debate between mathematical formalism and realism. Whether we eventually adopt new axioms or accept a multiverse of sets, the continuum hypothesis defines the edge of logic. Cantor's initial question about the size of the continuum has transformed our understanding of the infinite and the nature of proof itself.